Good morning, all. Is my screen visible? Okay. So, in last lecture, we started with the point processing operations or piecewise linear operations first on the image to transform or to enhance the intensities present in the input image. And there we started with the thresholding and contrast stretching operation. We started with thresholding basically, and we saw that here, if you see, we were given with the input image having intensities R. We convert those input intensities to the output intensities S with the help of some transformation. We call that as a S is equal to transformation on R. Okay. So basically in a thresholding, what we do is we choose some intermediate intensity level, let's say M, and with respect to that intensity, whatever input intensities you have above M, you mark those to the intensity S with some higher value. Let's say this is equal to L minus 1 value, and whatever input intensities you have which are lesser than M, you consider them as an output intensity 0. And at M, at intensity M, you have sudden transition. So just before M, all the pixels will be shown by the dark black color, and just after M, all the pixels will be shown by the full bright color or white color. And this way, your input image will have various intensity levels, but the output image will have only two intensity levels, either full black or full white, and dark and bright color intensity. And that is called as thresholding operation. So you choose some threshold value M, and you convert your input image to the two level image in the output, and the result is a binary image. Okay, we saw that if you don't want to suddenly transit from the pixel having, suppose this is your M, this is somewhere your M, let's say M is equal to 150. So the pixel having intensity, let's say 149, pixel having intensity 149, and after M you will have some pixel, let's say having intensity 151. So as you can see, pixel intensity 149 and pixel intensity 151 are not so differentiable by the naked eye. Okay, they are not having a much difference in their intensity, but because of thresholding, this pixel will be marked to the black or the dark color, and this pixel will be marked to the bright color or bright intensity. This will be converted to the dark intensity. So as we can see, even if those are close in the intensity in the input image, but in the output image, this will be dark and this will be bright. If we don't want this to happen, if we want, there should be the slow transition of the intensities from the pixels which are close to this M, for all the pixels which are close to this M. If I want slow transition, then instead of having this sharp vertical edge like this, we can have a smooth increasing edge like this, as you can see here. And what result we will get in the output is called as a contrast stretching. So we can basically say that thresholding is a subtype of contrast stretching, where you stretch the contrast at a sudden boundary, where at M equal to something, some threshold. But here what you are doing, just before M, you are converting to some intensity value. So just before M, you are marking to some intermediate value. Just after M, you are marking to some other intermediate value, which are separated by some value. Further, if you go beyond M and after M, then you will see that you are again marking them to some intensity value. So if you see here, uh, when I consider this pixel and this pixel, the separation was small, but here the separation was little more. If I take the next pair of pixels, let's say pixel here or pixel here, it is it is having somewhat larger separation. But when I converted to output image, the separation got even more larger. So what I'm doing is all the samples close to the M, which are separated by small distances, I'm I'm moving them farther away with respect to intensity M. So this is the intensity M on input image. I will erase everything and I will clarify once again. So in an input image, you have an intensity M. In an output image, you mark that intensity to M itself. So input image having intensity 150 will be converted to the output image having intensity 150. So input and output will have same intensity at the threshold. Just before threshold, whatever intensity you have, you will reduce that intensity here. And just after threshold, whatever intensity you have, you will give boost to that intensity. And that's how the closer samples are now you are spreading away in the output image. So you spreaded away these intensities in the output image. In the input image, they are very close. As you can see, in the input image, they are very close, but in the output image, you spread them. And that's why it is called as contrast stretching. So the contrast means the separation between dark and bright color. You increased that separation between dark and bright color, and hence we call it as a contrast stretching. Okay, and we discussed this in the last lecture. So from here, we will go ahead and we will see few more points about the contrast stretching. It is the simplest method of piecewise linear function, as we say. It is linear from here to here. It is linear from here to here, but it is kind of non-linear from here to here because it is a kind of curve. Instead of this, if I use a straight line, for example, let me erase this now. Instead of having this kind of shape, if I have this kind of shape, let's say from here to here a constant line, from here to here a constant line, and from here to here a straight inclined line. Then I have a straight line here, so this is linear. I have a straight line here, this is also linear. I have a straight line here, this is also linear function. So these are three pieces of a linear function. So I can call this as a piecewise linear function. So it is a simplest piecewise linear function, which is nothing but a contrast stretching operation graph. A low contrast images result from the poor illumination, lack of the dynamic range in the image sensor, or wrong setting of the lens of the aperture during the acquisition of the image. So there may be various reasons why you have a low contrast image, why your image looks like a bright or dark image. The reasons may be any one of these, but by using contrast stitching, we can make it better and we can improve the dynamic range. We can make dark samples more and more dark and bright samples more and more bright, and hence we can have a spread of very dark to very bright intensities, and the image will look better. So I will explain that with the help of this example. As you can see, we have just concentrate on this graph. Just concentrate on the graph which is on the top left side, the very first graph which shows the transformation from the input image to output image. So this side indicates the input intensity levels. This indicates the output intensity levels. R and S, as you can see, R is the input intensity, S is the output intensity. And this is the graph which shows the transformation, how contrast stretching function is being operated. So you see here there are 2 points. One is here with the input intensity R1 and corresponding output intensity S1. And there is one more point here with the input intensity R2 and corresponding output intensity as S2. Okay, so let's discuss about these 2 points. Lower one is R1 S1, upper one is R2 S2. Okay, so figure shows a typical transformation used for contrast stretching. There are 2 points R1 S1 and R2 S2 which controls the shape of the transformation. So by moving these 2 points R1 S1 and R2 S2, we can change the shape of this transformation. I hope you can understand this. You can imagine as if this is the rubber band between this point and this point, and you are holding that rubber band at these 2 points R1 S1 and R2 S2. So if you change those two locations, the shape of that rubber band may be flexibly changed. So you can control the shape of the transformation. Now, if I consider R1 is equal to S1 and R2 is equal to S2, what does that mean? Suppose this is your graph. R1 is equal to S1 means what? Height here 0 to R1 and 0 to this height 0 to S1. These two are same. So this much is same as this much. Okay, R1 is equal to S1. And another point R2 is equal to S2. What does that mean? That means you are holding to those. Let me reshape this. R1 is equal to S1, R2 is equal to S2. This is R2 and this is S2. So when R1 is equal to S1 and R2 is equal to S2, that means these 2 points are actually making this line to pass in a straight line, making to pass through these 2 points and without any inclinations, any additional inclinations. So we can say that the transformation is linear function that produces no changes. So you have point R1, you mark it to S1. As I said, R1 is equal to S1, I can call this as a R1. As I said, R2 is equal to S2. So if this intensity is say let's say 100, then S2 will be also 100. Meaning of this is whatever intensities you have in the input image, the same intensities you will get in the output image because there is a straight line mapping between input and output. If you have 50 intensity here, corresponding intensity in output also will be equal to 50. Okay, so you have no changes in the gray levels. Now, if R1 is equal to R2, what will happen? Let's analyze that scenario. If R1 is equal to R2, means what? R1 is equal to R2 and S1 is equal to 0 and S2 is equal to L minus 1. R1 and R2 are two different points, but I am assuming that I am connecting them. This is how I connected and I made R1 is equal to R2. But in this case, this is my S1 and this is my S2. And what they are saying, do not use this scenario. Use R1 is equal to R2, but use S1 is equal to 0 and S2 is equal to L minus 1. So I will redraw this and I will make R1 is equal to R2. Let's say this point is R1 equal to R2 and corresponding S1 in this case is 0 and this is the output. So you can see here as I have only one point uh, on the horizontal axis, that is R1 equal to R2, but there are two intensities on the vertical axis. The lower I am calling S1 equal to 0 and the upper intensity I am calling S2 is equal to the largest intensity possible that we can have, L minus 1. So you see that S1 is equal to 0 and S2 is equal to L minus 1. So this way, if we have a graph, then what is this? This is basically what we have learned earlier. That is nothing but the thresholding operation. And we have already discussed that in previous slide. I moved from thresholding to contrast stretching, and there I told you that if you don't want to have same threshold, so that the pixels which are very close should not be separated from mm, total dark to total bright. If you want a smooth transition for the pixels which are near this threshold, then you use some kind of inclination like this. So what basically you do is you use a lower threshold which is R1 and you use upper threshold which is R2. So this is a basically graph when R1 and R2 are separate. This is a contrast stretching. But when I say R1 is equal to R2, I go back to the thresholding operation. So that is what is being shown here. If R1 is equal to R2 and S1 equal to 0 and S2 is equal to L minus 1, that is basically a thresholding function which creates a binary image, which we have already discussed earlier. So now let's discuss what happened in the resulting image when I perform the contrast stretching. So intermediate values between R1 and S1 and R2 and S2 will produce the various degrees of spread in the gray levels of the output, and hence it affects the contrast. In general, R1 is less than R2 and S1 is less than S2. See, if I take R1 greater than R2, suppose this is my point R1 S1, okay, and someone chooses a value of R2 which is somewhere here, and this is the maximum point. See what I'm doing. If I choose value of R2 here, this is R2 comma S2. So what will happen? Uh, if I choose R1 larger, as you can see, it is larger on the horizontal axis, and R2 is lesser. As you can see, R2 is lesser on the horizontal axis. R1 is larger here. So if some intensity, for example, in between R1 and R2, इथे असेल, for example, then what will be the corresponding output intensity? So you have to mark this line upward, or you have to project this point upward, and now you can see that there are two intersections. One is here and one is here. What will make you decide what is the output intensity? Whether this is the output intensity or this is the output intensity. So this is not a correct graph. This is a wrong graph having ambiguity, and this is not giving one-to-one mapping. So this kind of graph is avoided. And to avoid that, we must have the R1 less than equal to R2 and S1 less than equal to S2. Then only we will have a single valued function, and each intensity in the input will be marked to the each unique intensity in the output. Otherwise this kind of problem will happen, and hence the image resulting image will be completely wrong, and hence you have to choose values of R1 and R2 and S1 and S2 carefully before doing the contrast stretching. So here you can see that value of R1 is somewhere here and value of R2 is somewhere here. So R1 is less than equal to R2. This condition is satisfied. Similarly, S1 is here and S2 is somewhere here. So S1 less than equal to S2. This condition is also satisfied. Okay. Please type in a chat box. Have you understood up to this? Please type in a chat box. Hello.
Yes, sir.
Okay. So after that, here are the examples. So you first see in a part A, it is a transformation function or the contrast stretching uh, transformation graph is shown. In the part B, a low contrast image is shown. Low contrast image means what? The original image where everything looks dark, dark. Can you see this second image? This image, everything looks dark, dark, and it is a very dull image. It does not look good at all. So what you need to do is you need to introduce a contrast stretching here because there is no bright part available. The white color is not so visible. The colors are very crowded near darker side. So you apply the contrast stretching operation, and if you apply that contrast stretching operation, you will get the resulting image which is shown in the C. So as you can see, this is the layout. This is how you have to look at these images. A is the top left, B is the top right, C is the bottom left, D is the bottom right. Okay. So you apply the contrast stretching and you see a very good image here. If you further apply the contrast stretching with the logic that we understood, that is, see, this is your input and output axis. If you apply contrast stretching like this is suppose point R1, this is point R2, S2, you will get some image. Then I will sketch one more time. This is one other kind of shape, and this is some other kind of shape. So what basically I am doing is, if you look at this image, R1 S1 and R2 S2 are separated by a large amount in the horizontal axis. So you see the inclination here is a smooth inclination. So in this case, you will get a less contrast stretching. If you see this another graph here, inclination is increased. You will get a more contrast stretching because point R1 S1 and point R2 S2 come close in the horizontal axis. Okay, and if you see at this third image, R1 S1 and R2 S2 are on the same vertical line. That is, separation between R1 and R2 is very less. In this case, you will get the maximum possible contrast stretching, and we already know the name of this transformation, which is called as thresholding. So if inclination in this part, inclination in this part is increased, the image will look more and more contrast stretched. And this is the last possible contrast stretching that we can have with the help of thresholding operation that you can see here. So you can see the D graph is result of thresholding operation. And that has been shown here because thresholding is a special case or the subset of contrast stretching, and that's why it is shown here. I hope you can make out the difference. The description of what I just uh, uh, said is available on this slide. So you can see in the last graph we have R1 is equal to R2 is equal to M. That is the constant threshold value, and hence the image which we see in the last graph is a binary image. Okay, and rest of the discussion that we already have had is available in this particular slide. You can read that. Basically, the original image which was used here in this analysis is the result of scanning of pollen under the electronic microscope. So you scan the pollen grain under the electronic microscope, and what is seen, the digital image of that is magnified 700 times, and then you get this image. Okay, and it's not so good, so you digital process that image for image enhancement using contrast stretching, and you get this. So this is pollen of sunflower. After thresholding and contrast stretching, we have third category of piecewise linear transformation, that is gray level slicing. So we will see what is gray level slicing. It is often desired to highlight a specific range of gray values in an image. So what I am talking about is, don't contrast stretch that image, just highlight specific range of gray values. For example, suppose this is my image, actual data in my image lies between say 50 to 130. So you enhance or you amplify the gray intensities between this range, and you keep all the gray intensities either constant, or you reduce them. Both way you can do gray level slicing. So this is called as slicing of a gray levels. You take a slice of a gray values between 50 and 130, and you provide the amplification to those gray intensities, and rest of the intensities you can keep unaltered or untouched. And application include enhancing the features such as masses of water in a satellite image, or enhancing the flaws in X-ray images. For example, suppose you want to see the blood veins in your body. So what is generally done is, a person is allowed to swallow some kind of metallic liquid having a very small amount of silver or any other ingredient, which can be digested in a few duration. Some kind of metallic liquid he is allowed to swallow. Then that liquid will flow through all the veins, and then some kind of imaging, X-ray or uh, gamma ray kind of imaging is done on that person. And on the electron, after doing that imaging on the image screen or the digital screen, you will be able to see all the veins or the all the blood veins of that person through which that fluid is flowing, because that is a metallic fluid that can be easily detected through the X-ray or gamma ray imaging. And when you see that fluid, and the rest of the part of the person and the background will be of very low intensity, let's say dark intensity. So if you want to highlight all the veins, if you want to highlight all the veins of that person, what you will do is, you will highlight all the gray levels containing the part of that metallic fluid, or uh, all the intensities which are lying in the range which is corresponding to the veins. You will highlight only those intensities, and the rest of the intensities you will keep untouched. So there are several ways by which you can do this. Most of them are variations of two basic themes. One is to display the high value for all the gray levels in the range of interest. So one solution is, you take the intensities which are under interest. For example, from here to here, these are the intensity values. I want to suppose this is in general transformation from gray level R to gray level S. This side is R and vertical axis is S, and I want to convert all the R values to S values depending on intensities. And I see that in between this to this range, I want the data to be sliced or enhanced. So what I will do, I will introduce high boost to all the intensities between this range, and this is one of the choice. Okay. Other choice is, you in between these 2 points, you enhance the intensity of all the pixels, and before and after this you keep the intensities constant, or you can keep the intensity here at a constant value. Okay, so we will see graph later in the next slide. So the transformation shown in figure A in the next slide is the example that I was talking about. As you can see here, we are interested in the intensities of pixels between point A and point B. So all the pixels having intensity in between A and B, they are converted to the output intensity, let's say this value. And all the pixels below intensity A and above intensity B have been mapped to the output intensity of this value. So basically what we will have is a uh, output image having either this intensity value or this intensity value. So only two intensity value you can have. Okay. Other graph is you have a input image, you want to transform that to output image. So transform all the pixels before A to the same value. Suppose here you have intensity 50, you convert that to the output intensity 50. After B, suppose somewhere here you have the intensity 129, you mark that intensity to 129. So what I'm doing, just before A, whatever intensities we have, we are converting the output image having same intensities. Whatever intensities after B we have, we are maintaining all those intensities. So that's why you can see this kind of inclined line, because I want to maintain all the intensities after B and before A. But in between A and B, what I am doing, actually this graph should be like this. Mark all the intensities as it is. If you want to get the same output image as that of the input, then the graph should be like this, whatever I have shown by the dotted line. But I don't want to have the same image. What I want all the pixels in between A and B to be highlighted. So that's why I take this slice and I converted those pixels to the high intensity. And as you can see, output intensities will be this for the all pixels between A and B. And this is the other way how we can do the gray level slicing. So in this case, I give no much importance to the pixels before A and after B, and hence this is called as intensity or the gray level slicing without background. So background is not so given importance. Background is just kept to the darker end, and only point of interest or the data of interest is only highlighted. Okay, in between A and B. So this is called as gray level slicing without background. And in the other case, you see that data of interest is highlighted as well as background is kept untouched. Background is not altered. Background is not attenuated. Background is kept as it is. So this kind of transformation is called as gray level slicing with background. So background is kept maintained, and at the same time, interested data is highlighted. So that all is discussed in this particular explanation. As you can see, what we saw on the next slide about all those images, all those four graphs, the discussion is shown. So figure A is the transformation range highlighting image. Figure B is the transformation highlighting range AB, but preserves all the other gray levels. That means it preserves the background. Figure C is the input image, and figure D is the result of using the transformation on it. So this is the input image. This is the input image, and if you apply the transformation on this input image, as you can see, what is that? C. Image C is the input image. Image C is the input image, and image D, that is this, that is nothing but this. So image D is the result of using transformation in A. So which transformation? This transformation they have used. That is gray level slicing without background. So as you can see, the gray level intensities of these two horizontal lines are only highlighted, and these gray level intensities which are less than or greater than B, less than A or greater than B, these intensities literally disappear. So you can see there is no intensities available here. They are only dark blackish color. Why is it so? Because only this part falls between A and B, and rest of the part falls just before A or after B, and that's why they simply are made of some dark shade like this level. Okay, so this is the this is the gray level slicing without background. I will show you one example where gray level is sliced, but background is also preserved. That is called as gray level slicing with background. I think I have copied that image here itself. So let me show you here itself. Yes. So in this case, this is the input image. As I explained earlier, one of the example where you want to trace all the veins from the blood or the blood veins from the human body. So this is actually a kidney image where you want to visualize all the blood veins near kidney part, and you can see the first input image looks a dull input image. There are no much details available in this image very clearly. So if I perform the gray level slicing without background, it looks like this. So as per application, either you can use this image or you can go for intensity slicing or gray level slicing, keeping the background or preserving the background. So background is preserved in this case. So as you can see, all the intensities in between A and B, all the intensities in between A and B are highlighted, and before A and after B are kept as it is. So it's like this. So what you see here, darker shades are at the intensity level, this intensity level, and what other gray levels you see are just because they are lying before A and after B, and they are carrying the same intensity as that available in the original input image. One of the application of this where you need to keep the background I can give you is in a Google Maps. Everyone might have used Google Map. You can see here, this is Chhatrapati Shivaji Maharaj Stadium near Maruti Mandir area. If I highlight all the roads in this image, this is not actually a satellite image. It is a map image. Let's see a satellite version. Okay, this one. So here, some kind of image processing can be used to uh, highlight all the roads. And after that, if I keep only the road image, is it enough for you to understand from where you can go where? Unless this kind of some areas are not available, some kind of other maps, whether there is a building or whether there is an open space or whether this kind of some shade uh, and whether there is a greenery or water, this kind of background, unless this kind of backgrounds are not available, you cannot have a clear idea of which particular junction you are looking at and which particular road you are following, because otherwise all the roads look similar and you cannot trace that I came here after Maruti Mandir. Okay, so this first left might be near the Lotlikar hospital, then the next left might be near the Parkar hospital. So I cannot keep tracing all the time, isn't it? I should be able to get a clear idea just by looking at the image at the particular section of that image. So for that, I need to keep some amount of background. I cannot delete all the background data. And in such cases, you need to have gray level slicing, keeping or preserving the background. Okay. After gray level slicing, as we saw, we are discussing about the piecewise linear transformations. After gray level slicing, we have a bit plane slicing. The last one, piecewise linear transformation that we have is a bit plane slicing. The bit plane slicing is used It is used for separating a digital image into its bit planes, and it is used for analyzing the relative importance played by each bit of the image, a process that aids in determining the adequacy of the number of bits used to quantize each pixel level. For example, suppose I will give a brief idea and we will discuss this bit plane sizing again in the next session. Suppose this is my image having one pixel here. Let's say value of that pixel is 255 and another pixel here having value of 127. What is binary corresponding to 255? What is binary corresponding to 255? 1 1 1 1 1 1 1 1. And what is binary corresponding to 127? 0 1 1 1 1 1 and 1 1. So when this image is getting saved, you see that this pixel is having a very bright color, the brightest possible color. And that's why the MSB of this is 1, and it's according to the corresponding decimal representation. Decimal is 255, that's why the MSB came out to be 1. And in the next pixel, the decimal value is 127, the intensity value is 127, and that's why the MSB value came out to be 0. So if you see towards lower end, all the pixels are same. Towards lower end, from the pixel number 7 to bit number 7 to bit number 0, all the bits, my mistake, bit 6 to bit 0, all the bits are same. Bit 7 is only different. So what we can understand is bit on the MSB indicates the maximum amount of information from the image. For example, let's say one of the pixel has intensity 1 and other pixel has intensity 2 and other pixel has intensity 3. So what will be the input intensity level represented in a binary? In a binary, this will be represented as 0 0 0 0 0 1. This will be represented as 4 zeros, then 0 0 1 0, and the last will be represented as 4 zeros, then 0 0 1 1. Let's say one more, there is a 4, then that will be represented as all 4 bits 0, then next is 0, then next is 1, then next is 0, and then next is so if I compare some lower intensity value with some higher intensity value, what do I see? Even if I ignore this LSB, there is a difference in a MSB. Or let's say compare 1 and 4. 1 and 4. Where is the difference? If I say 0 0 0 0, if I compare only the bit position 0, bit 0, bit 1, bit 2. So bit 0, bit 1, bit 2, bit position 2. If I compare bit position 2 for this intensity and this intensity, I see that there is 0 here and there is 1 here. I'm not comparing LSB side. I'm not comparing LSB side. Then it will not lose much amount of data. This is what? This is decimal 0 and this is decimal 4. Okay. So as these numbers are very close, you can say that instead of 1 I have 0, so it is a big loss. You can say like this. But if I compare here, this is 255 and this is 127. If I compare at the MSB end, this is 1 and this is 0. and 127 is almost half of the 255 intensity. And because of that, if I compare only at the intensity level, that's enough to differentiate between these two images, or these two intensity values, isn't it? So bit plane slicing is basically you collect all the MSB bits from all the pixels. You collect all the MSB bits from all the pixels, and you make one image out of that image. So, like how I did here, you collect all the bit 2 positions for 0 and 4. Bit 2 positions make a 0 and 1. I will explain once again in the next lecture. And you make a one image. Then collect seventh bit from all the pixels. You can prepare one more image. Then from LSB, you make one more image. Likewise, from all 8 bits, you will collect from each pixel and you will make 8 different images. You will see that most of the image data will be available in the MSB bits from the image, and less amount of data will be available in the LSB bit formed image. And that's what we call as a bit plane slicing. So it's slice the bitwise and make the different images. We will see later in the next lecture. If you have any doubt, you can ask. Otherwise, I conclude the bit and can leave. Thank you.
Thank you, sir.
Any doubt?
No, sir, no doubt.
Okay, you can leave it then. Thank you.